Okay, I'm back with protractors. A protractor is used to measure and draw angles, and we'll talk more about angles in the next chapter. Right now, we're just looking at measuring them. The simplest kind of protractor is shown here. It's graduated in degrees with every 10th of a degree labeled with a number. In measuring or drawing angles with a protractor, be certain that the vertex of the angle is exactly at the center of the protractor. So what that's saying is right here. One side of the angle should be placed along the 0 to 80 baseline. So somewhere there, it could be on the left side or the right side. Notice that the protractor can be read from the 0 degrees point on either the right or left. So for this angle, it's less than 90 degrees, so you're reading counterclockwise, and it's going to be a smaller number. It's 50 degrees. While if you were measuring, say, let me get rid of that. This angle, then you would start and measure clockwise, and it's greater than 90 degrees, so you want to read the number that's bigger, 110 degrees. A bevel protractor is useful in shop work because it can be adjusted with an accuracy of 5/10 of a degree. The angle being measured is read directly from the movable scale. And a Vernor protractor gives you even more accurate measurements. It can be used with the accuracy of 1/60th of a degree, or 1 minute is what we call it, because 60 minutes is equal to 1 degree. And I know if you've not ever heard of that before, it sounds funny, but that's just part of the way we measure angles. We measure them in degrees, minutes, and seconds. And 60 minutes is a degree, 60 seconds is a minute. Doesn't have anything to do with time. That's just another way we use those words. And here again, I have provided a video on how to use a protractor. For example, rate 8, we're going to read the Vernor Protractor. So first of all, we want to look on the main scale up here at the top. And you can see we're looking at where the 0 hits. And you can see that 0 hits at about 42. It doesn't quite hit 43. So we go for the lower number. So we have 42 degrees. And then we look on the Vernor scale and see where it matches up exactly. And it appears that it matches up exactly here at the 45. So this Vernor protractor is measuring 42 degrees and 45 minutes. Meters with uniform scales. So we're not talking about meters as in a length measurement now. This is different. Many measuring instruments convert the measurement into an electrical signal and then display that signal by means of a pointer and decimal scale. Instruments of this kind, called meters, are used to measure electrical quantities such as voltage, current, or power, and other quantities such as air pressure, flow rates, or speed. As with length scales, not every division on the meter scale is labeled, and practice is required to read it correctly. The range of a meter is its full scale or maximum reading. The main divisions of the scale are the numbered divisions. The small divisions are the smallest marked portions of a main division. And on a uniform scale, all marks are equally spaced and all divisions represent the same quantity. So, for example 9, we want to read this voltmeter. And there's not really a measurement here. It says the range is 10 volts. So you can see that from 0 to 10. The main division is 1 volt. So it's divided up by every 1 volt. And the smallest division is in between each of those. There's a half of a volt. A dual scale meter has an upper and lower scale that allows the user to switch ranges as needed. Example 10 says, look at the following 2 meters. The one on the left reads exactly 4 volts. The one on the right reads 6.5 volts to the nearest scale marker, or maybe closer to 6.7 if we estimate between them. The smallest division is 0.5 of a volt. On this meter scale, the smallest division is 1/5 ampere. And the reason we say that is you have 1, 2, 3, 4, 5 spaces in there. Or it says 1/5 of 1/10 of an ampere, or 2/100ths of an ampere. The reading at A is therefore 0.2 plus 4 small divisions. So it'd be at A, it would be 0.2 plus 4 times 0.02, which would be 0.2 plus 0.08, or as it says, 0.28. The reading at B is 0.4 plus 3.5. See how it's 1, 2, 3, and it's in between 3.5 small divisions, or 0.47 ampere. So you would say that as 0.4 plus, you've got 3 divisions, so 3 times 0.02. And so that would give you 0.2, I wrote that wrong. That should be 0.4. 0.46, but because it's one more piece over, then we can say we're adding another 100th to get 0.47. On a non-uniform scale, spacing between divisions changes at various places along the scale, and the number of units represented by each small division also changes. The following ohmmeter scale is an example of a non-uniform scale. And this little guy here, that is an ohm. It's another Greek letter. It says, notice that between 0 and 5 ohms, each 1 ohm range contains 5 subdivisions. So between here and here, there's 5 subdivisions. 1, 2, 3, 4, 5. So that each of these small divisions represents 0.2 of an ohm. However, between 5 and 10, each 1 ohm range contains just 2 subdivisions. And of course, I've marked this wrong. The between 0 and 5 was from here to here. And each mark has 5 in between. Okay. And then between 5 and 10, between each mark, between each larger, is just 1. So therefore, each of these small divisions represents 0.5 of an ohm. As you move from right to left, the scale continues to compress, with each small division representing a larger number of units. This table gives us the value of the subdivisions for each part of the ohm scale. Number 11, we're going to read this. So first of all, the needle points to the second small division between 3 and 4. So here we've got 2, there's 3, and there's 4. So we start with 3 ohms. And we'll add to that the divisions past. So there's 2 marks past that 3 there. So we'll take 2 times 2/10 of an ohm. So that would be 3 ohms plus 0.4 to be 3.4 ohms. Let's try reading this one. So the needle points to the only small division between 30 and 40. So we start with 30 ohms. And there's only 1 mark between the 30 and 40. So it has to be at the 5. So we have 35 ohms. Next, meters with circular scales. Some meters have 2 or more circular dials, and each dial represents a different unit. To read these meters, you must pair the reading on each dial with its unit value, and then combine the results into a single measurement. So this water meter measures the number of cubic feet of water use. It contains 6 dials, each labeled with a power of 10, ranging from 1 up to 100,000. So to determine the number of cubic feet, read the dials in descending order, beginning with the 100,000 dial. So we would actually go the other direction. If the needle is between numbers, always read the smaller one. If it's between 9 and 0, read the 9. So let's read this meter. So we start with the 100,000. And it's between the 5 and the 6. So we read it as a 5. So that's 500,000. Then we go to the 10,000. And that is between the 1 and the 2. So we read the 1. That gives us 10,000. On the 1,000, it's between 0 and 1. So we just read it as 0. On the 100, It's between the 7 and the 8. So that's the 700. The tens dial between the 4 and 5, so we read that as 40. And on the ones, it looks like we have a 9. Add those up, you get 510,749 cubic feet. And you can see it's in cubic feet because of the units in the middle. Electric meters. Many electric meters also contain circular dials representing the number of kilowatt hours consumed. As with water meters, the dials represent powers of 10. On the following electric meter, the 4 dials represent the thousands, hundreds, tens, and ones digits on a 4-digit number of kilowatt hours. So for example 3, I change my colors back here. Read this number. So for the thousandth, we're between the 4 and the 5, so we're going to read that as 4. On the hundreds, we're between the 8 and the 9, so we're going to read that as 8. For the tens, we're between 5 and 6, so we're going to read it as 5. And on the ones, we are exactly on the 3. So we have 4,853 kilowatt hours. We're almost there, guys. Dial gauges, also known as dial indicators, are used to measure very small distances. They are useful to detect a difference in height along a flat surface, to center cylindrical stock, to monitor the depth of drill holes, to determine if the edges of a rectangular surface are parallel, and to perform many other precise measurements in machine tool technology, manufacturing, woodworking, designing, and automotive technology. And here are 2 metric dial gauges, and there is a video that I've included on how to use an English or a metric dial caliper. Says the metric dial gauges shown in figures C and D have 2 circular scales. Each small division on the larger scale represents 1/100th of a millimeter. The larger needle rotates either clockwise or counterclockwise. A clockwise rotation is considered to be positive, and a counterclockwise is negative, indicating that the object being measured is smaller than a standard or desired measurement. The arrows on the upper portion of the larger scales have been drawn in to indicate in which direction the needle is deflected. So what that's talking about is these arrows up here, whether it's going positive or negative. This one would be positive because it's counterclockwise. Clockwise would be, wait a minute, I said that wrong. Positive because it's clockwise. Counterclockwise is negative. So, for example 14, read this dial gauge. So the first thing we want to point out is this arrow up here. It's moving to the right or clockwise. So we know this is going to be a positive reading. The needle on the smaller scale, I'm looking at this one here, is between the 4 and the 5. So we pick the smaller one, just as usual, the 4. And that's read as 4 times 1, or 4 millimeters. Then the larger needle is reading 3132. And so we take the 32 and multiply by 0.01. Add these and we get 4.32 millimeters. Now, we're not quite done because we need to mark whether it was positive or negative, and since it's positive, we put a plus out front. For this dial gauge, first notice that we're reading to the left, so it's negative. Then read the smaller gauge. It's between the 1 and 2, so we read it as 1. And then on the larger, since we're going in a counterclockwise direction, as we move past 50, the number 40 actually means 60. So we're going this way, and so we have 50, and then this is 60, 70, 80, and 90. That's not an 80. There we go. I was thinking ahead to my mind. Okay, and so this dial is measuring 81 to 3. So 83 times 0.01 is 0.83 of a millimeter. Add these and we get 1.83 millimeters. But remember, because it's going to the left, we put a negative out front. Last topic. A U.S. customary dial gauge measures distances in inches. As with metric dial gauges, the smaller dial records the number of complete revolutions of the larger, with each revolution representing 1/10 of an inch. Each small division on the larger scale represents 1/1000th of an inch. And if it's going clockwise, then it's positive. Counterclockwise is negative. So let's read these two, and we will be done. First of all, the arrow is telling us it's going to be positive. Then we read the smaller gauge, which would be 0.5. Which is already written as 0.5 there, but anyway. 5 times 0.100 is 0.5 of an inch. And then we read the larger one. Now, since we're going clockwise and it goes past the 50, then this is 60, that's 70. So we're at 72. So when we add these, we've got 0.572 inches. And since it's positive, we put a plus out front. So it's positive 572 thousandths of an inch. Last one, this one, the arrow is moving counterclockwise, so that is negative. Read the smaller dial first, so we're at the 2. And we're going this direction, so it looks like 10, we're at 17. Add them, we got 217 thousandths of an inch in the negative direction. So that concludes this section and this chapter. So we'll start geometry next.